This is the experiment that laid the foundation for Einstein to develop his special theory of relativity. Well, actually, this is that experiment. It's called the Michelson-Morley interferometer, and the thing on my desk is similar, but I made some modifications so that I could play it like a musical instrument. Here's what it sounds like. This experiment actually failed to find anything, which sounds boring, but it's actually what makes it super interesting and probably the reason it won a Nobel Prize. When I say the ocean has waves, I'm talking about waves of water. When I say sound has waves, I'm talking about waves of air. A wave needs a medium in which to wave, right? But when I say waves of light, what's the medium? Scientists over like 100 years ago would call this luminiferous ether. And I don't know this for sure, but I have to imagine it was pretty obvious that it existed, because a wave needs a medium, just like sound needs air. That's what a wave is. It's the movement of the medium. If I was alive back then, I'd probably skip the Michelson-Morley experiment, because we know light is a wave, and obviously it's a wave of something. It'd be like checking if the sky was blue. But good thing I wasn't around to talk them out of it, because they found out there's no ether. How could that be possible? That's like saying there's waves in the pool but no water. It's pretty tricky to describe because light is made of something. It's an electromagnetic wave, and there are definitely electric and magnetic fields, but those fields don't need to be there in order for there to be a light wave. Light can just travel through nothingness. If that wasn't freaky enough, in the same breath, the Michelson-Morley experiment also revealed the speed of light is constant regardless of reference frame. And actually, that was the discovery that led Einstein to unravel our concepts of space and time. A common way to explain this is to imagine throwing a ball in a train. If the train's going 10 miles an hour and you throw a ball at 10 miles an hour in the same direction as the train, someone outside the train would say that the ball is moving at 20 miles per hour if they measured it with a cop's radar gun. That's because you were moving at 10 miles an hour, and then you gave it an extra 10 miles an hour by throwing it. But you would say it's only moving at 10 miles an hour if you measured it with your radar gun, because you and your radar gun are moving in the same direction as the ball, just not as fast. Okay, that makes sense. That's called classical relativity, because how fast the ball is going depends on the observer's velocity relative to the ball's velocity. If you're going the same speed and direction as the ball, you're going to say it's not moving. Okay, get ready to have your mind completely melted, unless you already know about this. If you imagine the same train scenario, but instead of throwing a ball, you turned on a flashlight in the direction the train is traveling, the light would fly from your flashlight to the other end of the train, just like the ball you threw. Here's the crazy part. If you measure the speed of that light and the person outside the train measures the speed of that light, you would both measure exactly the same speed. How is that possible? The person outside the train should say that the light is going faster since it's being added to the train speed. But that's just not how light works, and that's the result that came from the Michelson-Morley interferometer. With that information, Einstein's relativity just sort of falls out. Einstein was a genius, no doubt, but as soon as we found out the speed of light was constant, someone was going to discover special relativity. I don't think we needed Einstein for that. The equation for speed is just distance over time, like miles per hour. If we say the speed of light is constant no matter what, but two people say the light traveled two different distances in the same amount of time, that's where we have an issue. In the train example, the person inside the train says the light travels the length of the train, and the person outside says it traveled the length of the train plus however far the train moved in that time. If both people say the light was moving at the same speed but covered different distances, there's only one variable that can change to make this true, which is time. So time must have been moving slower for the person on the train, which sounds ridiculous, but time slows down when you go faster. In reality, space gets squished and time slows down for the person on the train. So maybe you started this video believing space was like a fixed grid and time moves at the same speed no matter what, but now you know both space and time both bend to the ultimate master of the universe, which is the speed of light. Actually, if you follow the math, it turns out if you're able to go faster than the speed of light, then you might be able to reverse the order of cause and effect, which would completely obliterate my last intuition about how the world works. But luckily, the speed of light is the speed limit, as far as we know. Okay, that was a bit of a tangent. I'll explain how these results came from the Michelson-Morley interferometer, and then I'll explain how to turn it into a musical instrument. First off, an interferometer is just a device that forces light waves to interfere with each other, which is a super useful way to measure really small movement. So we start by sending a laser into a beam splitter, which reflects half of the light to the right and lets the other half through. Then the two beams we split from the laser bounce off a mirror and come back to the beam splitter. Each beam gets split one more time, but the only thing we care about is the light that comes out of this side. So one beam takes this path, and the other beam takes this path. Which means in this region, we have two beams superimposed on each other. When lasers are superimposed like this, they interfere with each other. If the two beams line up perfectly, they add up. That's what's called constructive interference. If the beams are completely out of phase, they cancel each other out, and that's called destructive interference. You can actually see the light and dark bands where the superimposed beams either add together or cancel out. If we put a light detector called a photodiode, if we put that here, we can measure these light and dark bands. Light waves are super small, so the distance the laser beam has to move to go from constructive to destructive interference is about 100,000th of an inch. Since one beam travels this path and the other beam travels this path, I can change the length of one of these paths, and that'll change whether the beams interfere constructively or destructively. And remember, I only have to change it 100,000th of an inch because light waves are so small. I can just touch it and it'll change. And actually, it can even sense me walking around even though I mounted it on a big metal cube and suspended it by shock cords. Anyway, Michelson and Morley assumed that ether was this stationary ocean, like you can imagine air in a room. They figured that as the Earth orbits the sun, it should be moving through this ether. So they oriented their interferometer such that one beam would have to travel more in the direction of the Earth's orbit than the other. The idea was that if the ether was moving in the opposite direction of the wave, it should take longer for the wave to get to the detector, essentially shifting it backward. Then, if they rotated their experiment so that the other beam now has to fight against the ether impeding its movement, now that one should be shifted backwards. Transitioning between these two orientations should change how much the two beams interfere with each other, and that would change the light level, which we could measure with our photodiode. But, as we know, the speed of light is always constant, and there is no ether, so rotating the experiment did nothing. Okay, we can finally talk about how to turn this into a musical instrument. The only thing we have to do is mount one of the mirrors onto a speaker. Then, when I play my guitar, the path length taken by one of the beams is changed by the movement of the speaker. That means the beams will cycle through constructive and destructive interference due to my playing, and I can pick up the light here and output the signal as a sound. One cool aspect of this is how responsive it is to dynamic playing. So if I play softly, the speaker doesn't move a lot. So you can imagine one wave of my guitar string might correspond to going from constructive to destructive interference one time. In that case, the input and output should sound pretty similar. It'll just sound like a guitar. But if I play really hard, now the speaker is moving in and out really far. That means for every wave of my guitar string, the beams would cycle through constructive and destructive interference lots of times. Now my photodiode is picking up a higher frequency than what I put into it. And that means overtones. So the harder I play, the more overtones I get. And that's it. The guitar signal is being sent through and affected by the interference of light. And if light didn't behave like a wave, there would be no sound. Okay, so Let me know if you're interested in hearing about how I physically made this instrument. I'm thinking about making that video. I can also make a video about designing the circuit if you're interested in that. Otherwise, I'll just end this video with a song from my new album, Operaville, so you can hear the interferometer in action. It starts with the interferometer, and then this saxophone-like instrument called the glissetar comes in. I'm going to make a video that explains all the sounds in actually all the songs on the album. And in one of those videos, I'll explain what the glissetar is and why it sounds all wobbly. But for now, just enjoy the sounds.